It's all along the same argument. Okay? Same argument. But it's quite obvious that this is not quite clear, but all I'm saying is the principle of looking at the vibratory system using energy principle is another way to see the problem, and certainly we end up with the same carbon equation. Of course, it is not very well addressed or clear in this class to handle the damping power, right? So we reserve that for the next lecture. But all I'm saying is the principle. You have other fancy question? Okay. Then using the again same concept, considering total energy is there is energy due to mass, energy due to spring. Energy due to mass is 1/2 mx dot square, and energy due to spring can be written as 1/2 integration. I'm integrating from 0 to L because the spring is distributed from 0 to L. And the velocity, the mass of the spring is ms, and the dy over L. Ms is the total mass of the spring, and ms over L is mass per unit length. Okay, and then I have a length dy, so therefore this is the mass. And the velocity is y over L x dot squared. And then I want to integrate with respect to y from 0 to L, so this one and this one can come out, and this end up with 1/2 m plus 1/3 m s x dot squared. Yeah, that is correct. So, well, if we consider the mass of a spring, then only 1/3 of mass of a spring can contribute to the total mass of the vibratory system. So, for example, if I have this mass spring system, the mass of this one is about 300 grams. You feel this? Is this 300 grams? Heavier than, okay. This is a little bit heavier than 300 grams because the large orange is 300 grams. And this one is much lighter than this. And the contribution to the mass of the total system of this spring's mass is only 1/3, so can be negligible. Okay? Okay. What if we have the suspension? If you look at the suspension system of a car, you may see there is some spring, but you may see another component that is connected to the suspension system that may look like another spring. Okay, and you may consider that the deformation of tire that has another spring. Okay, when you model the suspension system, you can think there is many springs. And then you may think that, I can model this as is a mass, is a one spring, and another spring, and another spring, and that might connect it to another spring, and there is a spring, but okay. When you model some vibratory system, you found that there is many springs. And how does it vibrate? That vibrates exactly the same as the vibratory system which I just erased. I said the vibratory system that has equivalent stiffness. Okay? How can you get the equivalent stiffness? If I
do you consider the additional degree of freedom? Because it's not symmetrical, so you might rotate it.
that's another excellent question. So I will put that another excellent question to our bank again. Okay. We only consider this is a point mass. I only consider x over t. So degree of freedom, he knows very precisely the degree of freedom. Okay, how can you get KEQ? Okay, suppose, what is the equivalent stiffness that can replace K1 and K2? Suppose I have unit displacement over here, the deflection I have is K, the force I have is a K1 multiply 1, and the force I have is K2 multiply 1, right? But that is the force acting on this mass. And what about over here? If I have a unit displacement like this, then K3 and K4, what is conserved in K3 and K4? Force or displacement? Then I cut over here, and in the draw free body diagram, I will get the force acting on over here. And if I cut over here, I get the force acting on over here, the same as force acting on over here. So force is constant in this case. In this case, displacement is conserved. Using that concept, we can get the equivalent spring, like in this case, if there is a spring connected like this, then KEQ is what? K1 plus K2? Huh? Are you sure? Are you sure? 100 sure? Can you bet the 1만 원? Yeah, you learned this from high school and junior high school, right? And what about KEQ of this system? Things like this, right? I will demonstrate that we can actually use a spring, right? Very famous spring. 꼭 잡고 있어, 너무 안 돼. deflection like this, and you can experience the force, and then okay, same deflection, okay, and you feel much higher force.